Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronic Engineering. So in today's class, we are continuing to discussion on the question bank from the module 3, which is network theorems. So here, in previous class, we have discussed about the network theorem, the problems from the question bank on network theorems called superposition theorem, and Thevenin's theorem and Norton's theorem. So these three theorems we have discussed. In today's class, we are going to discuss about the Millman's theorem, Teligent's theorem, and maximum power transfer theorem. So first, let us go with the first problem, which is using Millman's theorem, determine the current through RL, which is the load resistance in the circuit, and the voltage drop. Okay, so R1, R2, R3, which are equal to 2 ohms, and RL is equal to 5 ohms, right? So what here we need to find? So find the voltage drop across the load resistance. Okay, so and also the current through the load resistance RL that we need to find. So here in the given problem, they have given the voltage, 3 voltage sources are there, and the voltage sources values are 4 ohms, 5 ohms, and 6 ohms, and these voltage sources having their internal resistance, namely R1, R2, R3, and in the problem they have given the values of R1, R2, R3 also. So here R1, R2, R3 values are the 2 ohms, and then RL value is the 5 ohms. So before going to solve this problem, so just let me remind what is Millman's theorem. So here, according to Millman's theorem, it states that the number of voltage sources are in parallel having their internal resistance respectively, or the number of current sources in parallel having their internal resistance respectively. Sorry, here the number of voltage sources are in parallel, and the number of current sources are in parallel having their internal resistance respectively. Then the arrangement can be replaced with a single voltage source in series with the equivalent resistance, or the current parallel with the equivalent resistance. So which means here, let us see here, let us see there are the voltage sources having their internal resistance are connected in parallel. Then we can replace this whole system, okay, and of course there is a load resistance here, let us consider, and we can replace this whole system, okay. So the parallel combination of the voltage sources with their internal resistance can be replaced with the, and other case, okay, if the current sources having their internal resistance, as we know already, the voltage source, the internal resistance of the voltage source in series with the voltage source, and the internal resistance of the current source is in parallel with the current source. Then suppose if there are these two possibilities, then we can replace this voltage sources with internal resistance connected in parallel, and the current sources with internal resistance are connected in parallel can be replaced with these two circuits. So which means here this total the parallel combination of the voltage sources with the internal resistance can be replaced, okay, with a single voltage source with its internal resistance and connected in parallel to the load resistance. The same way here, the current sources which are the current sources with internal resistance connected are parallel can be replaced with the single current source, okay, with the internal resistance should be connected in parallel with the RL, right? Then now how to find this V and R, right? So here V is equal to I into R, okay. Then here I is equal to V1 by R, V1 by R1 plus V1 by R2 plus V2 by R3 and so on into R equivalent. Then you can get the value of the V, okay. Then R equal to, anyway here R equal to R1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. So in this way you can find the R equivalent value, right? Then same way, suppose here if you want to find the I, then I is equal to I1 plus I2 plus I3. Suppose if the current sources with the internal resistance are connected in parallel, then here this current source, okay, the value of this current source or the single current source I is equal to, just add the the current sources present in the given network. Of course, again here the direction, the sign of these current sources is depends on the direction of the currents. Anyway, in this circuit, the direction of the currents is same. So that's why we simply just add I is equal to I1 plus I2 plus I3, because here I also we have considered in the same way of the I1, I2 and I3, right? Then that's what here 1 by R is equal to R1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. So by using this theorem, now we are going to find the current flowing through the load resistance. So in the given problem, which is similar to the case 1. So which means here the voltage sources, okay, having their internal resistance connected in parallel, so that we can replace this total circuit with like this here. So we can replace this total circuit here. So the internal resistance and the voltage. So let us consider here it is equal to R and here it is equal to V. Then here the RL is as it is. So this is RL. So let us consider here this is the current flowing through RL I. So what we need to find now, we need to find the value of the I. So from this circuit, so I is equal to the total voltage V by, so here R plus RL. So now what we need to find, because RL that we know RL is equal to in the given problem 5 ohms. So now we need to find the V and R value. Okay, so just now we have seen how to find the V and R value, right? So here first let us find R value. So here R is equal to R1 by R equivalent, which is equal to 1 by R, which is equal to 1 by R1. So all are 2, 1 by 2 plus 1 by 2 plus 1 by 2. Okay. So which means here 1 by 2 is here 0.5 plus 0.5 plus 0.5, right? So here it is 1.5 ohms. This is 1 by R equivalent. So then R is equal to 1 by 1.5. So which is 10 by 15. Okay. So ohms, right? So this is the R value. Then similarly, we need to find the V value. So according to this Milliman's theorem. So here how to find V? V is equal to V1 by R1 plus V2 by R2 plus V3 by R3 into R equivalent. So here V1, which is 4 by 2. So which is here, which is V is equal to. So V is equal to, so 4 by 2 here plus, okay, 4 by 2 plus, and here it is 5 by 2 plus, here it is 6 by 2 into 6 by 2 into what is this R equivalent? So here 10 by 15. Then this will be equal to, so 4 plus 5, 9 plus 6, here it is 15. So 15 by 2 into 10 by 15. So here 15 gets cancelled and 2 5s. Then here it is equal to 5 volts, right? So here the voltage V is equal to 5 volts. Then substitute here. So here V is equal to, let me write here the values. So in this equation, so V is equal to here 5 volts and here R is equal to here 10 by 15 ohms, and then here RL, which is equal to 5 ohms. Then find I. Then substitute these values in this equation. So here I is equal to, so what is V here? V is equal to 5 by, so 10 by 15 plus RL is equal to 4, right? So this is way we can find now if you simplify, then you will get the value of the I. So this is how we can find the current flowing through the load resistance by using the Milliman's theorem. Suppose here if you are having a current sources, then this equivalent circuit will become like this. So anyway here the current source, right? And then here the equivalent resistance. Okay, so which means here it is I and here it is R and here it is RL, right? So then apply the current division rule, then you can find the current flowing through RL. Let us consider here it is what is that? Let us consider here it is I1 or IL. Let us consider. So IL is equal to the total current here. It is I into the opposite resistor. So here it is R. So R by R plus RL. So this is the way to find the current flowing through the load resistance if what is that? If the circuit having the current sources having their internal resistance connected in parallel, right? So now by using this procedure we can find or we can apply the Millman's theorem for any given circuit to find the current flowing through the load resistance. Next we are going to discuss about the Telligence theorem, right? So here verified Telligence theorem provide V1 is equal to 8 volts and V2 is equal to 4 volts and V4 is equal to 2 volts. Similarly here I1 is equal to 4 amperes and I2 is equal to 2 amperes and I3 is equal to 1 amperes. So before going to solve this problem, so first let us see what is the Telligence theorem. So here according to the Telligence theorem, first let me read the statement. So according to the Telligence theorem, it states that the summation of the power delivered is zero for each branch of any electrical network at any instant of time, right? So as we know, P is, the summation of the power delivered is zero. So suppose let us consider this is a circuit and here the summation of the total power across each element must be is equal to zero. So which means here, let us consider here, it means here it is plus minus. So let us consider here, this is the direction of the currents. Okay. So let me consider here it is I1, okay, the direction, or in another words, because let me consider here it is V1, okay, and here it is V2, and here it is V3, and here it is V4, right? Then the current here it is, let us consider I1, and here it is I2, so here it is I3. Let me consider, right? Then according to this Telligence theorem, so here anyway V minus, because the power, right? Okay, V into I1, sorry, because V into I is the power, so V into I1 minus, so V1 into I1 minus V2 I2 minus V3 I3 minus V4 I3 again, which is equal to 0, which means then the Telligence theorem has been proved. So according to the Telligence theorem, this is mean the summation of the power delivered is 0 for each branch of any electrical network at any instant. So which means here 1, 2, 3, 4 branches are there, and the power what is the delivered through this branch here it is V into I1 minus V1 I1, and the power delivered through this branch here it is of course as we know V into I, so here the voltage across R2 is V2 and the current flowing through R2 is I2. So the same way the other two elements also. So this is how we can apply the Telligence theorem or to prove the Telligence theorem by this equation, right? Then now we are going to apply the same thing to here. Of course here as you can see they have given the directions also, in each case, but here of course in some cases they didn't give, like I1 they have given, but we don't know what is I2 value here. So I2 let me consider, maybe this is the I2 value, this is I2, so I3 is there already and I4 is there and I5 is there and I6 is there, right? So in the given problem, of course V1 is also they have given V1 is equal to 8 ohms, and V2 is here this is the V2, okay, but here other values they haven't given. So but according to this theorem, okay, according to the Telligence theorem, so let me write here the equation, then after that you just substitute the values in that equation, then it will you will get the value as a 0, so that the Telligence theorem has been verified, like that we can say. So here V1 I1, and because first let me write here V1 I1 minus V2 I2 and minus V3 I3 and minus V4 I4 minus V5 I5 minus V6 I6, which is equal to 0. Okay, which is equal to 0. So then if you substitute all the values here, but in the given problem they have missed some values, so that's why it is very difficult to find, because here as you can see, what are the values they have given? I1 that they have given. Okay, so V1 also no. So let us write here 8 into, here I1 is 4 ohms, 8 into 4 minus here V2 I2. Okay, so where is what is V2 here? The value of the V2 is 4. Okay, and the value of the I2 is 2. So 4 into 2, let me write here. Then 4 into 2 minus V3 I3. So here V3, we don't know the value of the V3. Okay, and even though here the resistance V3 5 ohms. Okay, fine. I3, okay, I3 is there. Right. Let us consider here the R value across. I mean, this resistor is equal to 5 ohms. Then we can find, because V is equal to I into R. Right. So here I is equal to the I3 value that they have given 1 ampere, and R is equal to 5. So here then the value of V3 is equal to 5 volts. Right. So 5 into here V into I3 is equal to 1, right? Then V4 I4. So V4 is equal to 2, and I4. So I1, I2, I3 only that they have given, then I4. So as we know here, I2, I3 that we know, because let's just apply here the KCL. Okay, so according to the KCL here, what is the entering current? I2. Okay, and I3, I4 are the leaving currents. So I2 is equal to I3 plus I4. So then according to this, I4 is equal to I2 minus I3, right? So we know I2 value and I3 value. So I2 is equal to 2 and I3 is equal to 1. Then I4 is equal to 1 ampere. Then here V4, 2. So 2 into 1 minus, then V5. So V5 also we don't know V5, the value of the V5. Okay, and but we know the value of the I5. So I5 also we don't know. So again here the value of the I6 also we don't know. But here again if you apply here the KVL, because we know I1 and I2, then I6. So if you apply the KCL at this particular point, then here I1 is leaving current, and all are the leaving currents. Okay, I1 plus I2 plus I6 is equal to 0, right? So here I6 is equal to minus I1 minus I2. So here I1 is equal to 8 ohms and I2 is equal to I1 is equal to 4 and I2 is equal to 2. So here minus 4 minus 4 and minus 2, so which is minus 6 amperes, which is I6 value, right? Then similarly what is the other I1, I2, I3? So now I4 value. So I4 just now we have calculated, I4 is equal to 1 ampere. Then similarly I5 also we can find. So because now apply the KCL at this particular point, right? So at this particular point, then what are the entering currents? Entering currents are here I4 and plus I6, which is equal to the leaving current, here it is I5. Then I5 is equal to I4 value, I4 is 1 and I6 is minus 6. Then here I5 is equal to minus 5 amperes. So like this you can find the remaining current values and as well as the remaining voltage values. So then by now we know all the values of V1, I1, the voltage across each element as well as the current flowing through each element. Then substitute all the values in this equation, then you will get 0. Right? So don't get confused because some values they have not given. Okay, because by applying a simple network reduction techniques, so we can get the values of the other currents and other voltages also, because that they have given this is the 5 amperes across this and this, right? So then by using this you can find the remaining the voltage across the remaining elements as well as the current flowing through the remaining elements. So this is the way to verify the Telligence theorem, right? So now I think everybody would get understood how to apply the Telligence theorem, so that we can apply this Telligence theorem for any given network, right? Yes. Now let us move to the the other network theorem, which is the maximum power transfer theorem. So here, find the load impedance in the below figure for the maximum power to the load and find the maximum power. Right. So this is the problem. So before going to the problem, so let us recall what is the maximum power transfer theorem. So according to the maximum power transfer theorem, it states that, of course, a linear and bilateral network. So maximum power is delivered to the load when the load resistance is equal to the internal resistance of a source. Right. So the condition to get the maximum, or the condition at what condition the maximum power delivered to the load, here it is, when the resistance is, or when the load resistance is equal to the internal resistance of the source, then the maximum power will be delivered to that particular load. Right. So this is the condition to deliver the maximum power to the load. So based on this condition, now we are going to find the load resistance. Right. So which means to find the load resistance, first we need to find the equivalent resistance, which is nothing but the Thevenin's resistance. Right. So that is what here Rs is equal to RL. When Rs is equal to RL, here Rs is the Thevenin's resistance. Okay. And RL is the load resistance. So when Rs is equal to RL, then the maximum power will be delivered to the load, which is RL. Then what is that maximum power? That we can find by using this equation, because in the previous case, when we are discussing about the Thevenin's theorem, we have already discussed how to find the current flowing through that particular load resistance. Then, of course, as you know, P is equal to, V square into I square into R. So in both the way, you can find the power. So suppose if it is a V square into I, Vs means nothing but here the, what is that? Vs is nothing but the Thevenin's voltage. Okay. And RL is nothing but whatever the load resistance that we are considering. So which means RL is equal to R Thevenin's. So here, in this way, we can find the maximum power delivered to the load. Now let us go with the problem. Right. So this is our given problem. So in this problem, now we need to find what is the maximum power delivered to the load, and as well as we have to find the impedance also. What is, at what impedance the maximum power will deliver to this load. Right. So the same way, like this is AC circuit. Okay. So because the DC circuits we have already discussed in the previous classes, so that's why I have just considered an AC circuit to solve this problem. So first, what we need to do, just convert all the resistance and reactances into the impedance, so that it will be easy for us to solve the problem. So anyway, here also we need to find what is that, the Z Thevenin's and as well as the V Thevenin's. So for the Z Thevenin's is to find the value of the load resistance where the maximum power will be delivered to the load, and V Thevenin's is used to find, so what amount of the power, okay, what is the value of that maximum power delivered to the load impedance. That we need, for that we need to find the Z Thevenin's also, V Thevenin's also. So first, to find the Z Thevenin's, again the same procedure. Okay, so where we need to find the Z Thevenin's? Across the load terminals. And how we can find the Z Thevenin's? Again, by replace all the active sources by the open circuit or the short circuit. If it is a voltage source, then we should replace with the short circuit, and if it is a current source, then we can replace with the open circuit. So then anyway, here we are having only the voltage source, then the voltage source is replaced with the short circuit. Then here the Z1, which is equal to 6 ohms minus J8 ohms, and then Z2 is equal to J8 ohms. So this is Z1 and Z2. Now this is the the equivalent circuit to find the Z Thevenin's. So from this figure, you can say Z1, Z2 are in parallel, so that here the Z Thevenin's, which is equal to Z1, Z2 by Z1 plus Z2. Then substitute the values of Z1, Z2 here. So here Z1 is 6 ohms minus J8 ohms into here Z2 is J8 ohms by Z1 again 6 ohms minus J8 ohms plus J8 ohms. So just simplify this, then you will get finally the value here. It is 10.66 ohms plus J8 ohms. So this is the Z Thevenin's value. Right. So now next we need to find the V Thevenin's value. So for the V Thevenin's again the same way. So first, this is Z Thevenin's we have calculated. Then V Thevenin's here, how to find again, where to find the V Thevenin's again across the load terminals. Okay, so now we need to find the V Thevenin. So here the E Thevenin's or V Thevenin's is nothing but the voltage across the impedance Z2, right? So for this you just apply the voltage division rule. So by applying the voltage division rule, we can get the value of the E Thevenin's, which is the voltage across the impedance Z2. So then here E Thevenin's, which is equal to, so the total voltage here it is E into, so Z2 by Z1 plus Z2, right? Then substitute the values here. So what is E? 9 volts at an angle of 0 degrees. So here it is equal 9 at an angle of 0 degrees into here Z2 is equal to Z8 ohms by Z1, here it is, let me see, Z1 is 6 minus J8 ohms, 6 minus J8 ohms plus J8 ohms. Then if you simplify, then you will get the E Thevenin's value, right? So once we find the E Thevenin's and Z Thevenin's value, right? So then what is the value of the P? P is equal to I square R. So R is nothing but, because then what is, according to this here. So now what is the ZL value? So here ZL is equal to what is that? Z Thevenin's, which is equal to 10.66 ohms plus J8 ohms. So this is the load impedance. So this is the load impedance value, right? Because they given the condition for the maximum power to the load. So the condition to get the condition to deliver the maximum power to the load is nothing but the ZL is equal to Z Thevenin's, right? Now I square R. So how to find I then? Because as we know already, let me write here. So this is the Z Thevenin's, and here it is the E Thevenin's. Okay, and here it is, and here it is ZL. This is ZL. Okay, then here the current, here it is. Okay, so then I is equal to, what is I is equal to V by R. So E by, anyway here ZL is equal to Z Thevenin's. Okay, so 2 into Z Thevenin's, right? Then R means here anyway now I square Z, because here we are considering in terms of the impedances. Then Z, now we know, okay, the Z is nothing but our Z Thevenin's. So from here you can calculate the I value, then substitute I value here and substitute the Z Thevenin's value here. Then you will get what is the maximum power flowing through that particular load resistance, right? So this is how we can apply the maximum power transfer theorem. Yes. Now let us go with another problem. This is also from the maximum power transfer theorem only, based on maximum power transfer theorem. So here also the same things that we need to find. So first we need to find the load impedance, and as well as we need to find the what is the maximum power delivered to the particular load impedance. So here also the same procedure. First we need to find the Z Thevenin. So the Z Thevenin's will be the load impedance. Then after that we need to find the V Thevenin's. Then by using the Z Thevenin's and V Thevenin's, we can find the maximum power delivered to the load impedance. So again Z Thevenin's, where we need to find the Z Thevenin's? Across the load terminals. So here ZL is the load. So that's why first we need to find the Z Thevenin's, okay, across the load terminals, which is ZL. Then by replacing the voltage sources with the short circuit, and because anyway here only voltage sources are there, so the voltage sources has been replaced with the short circuit, right? So first let us find the Z Thevenin's value. Okay, so here to find the Z Thevenin's value, here of course the same way, here first we need to write what is that, the Z1, which is nothing but J9 ohms, and Z2 is equal to also J9 ohms, and Z3 is also J9 ohms. And then because of course here anyway all they have considered as a Z1 because all the what is that impedance reactance are same values. So that's why Instead of Z1, Z2, Z3, they have considered Z1, Z1, Z1 because all are having the same 9 ohms reactance. And then Z2 is equal to, here it is 8 ohms. Okay. Then now this is the circuit. So anyway, here it is impossible to identify what are the two resistors which are connected in series or what are the two resistors which are connected in parallel, because of course these two resistors having one common point, but this common point is shared with the resistor Z2 again. Okay, so that's why what we are going to do here it is, so we are converting this delta into the star, so which means here like this. Right, so let me consider here, because of course all the resistors having the same value, so here also you will get the same values. Okay, so in the star also. So then here let us consider first Z is equal to here Z1, actually I mean in the regular way. So let me write here R1 is equal to, let us consider RA RB by RA plus RB plus RC. This is the usual formula from converting delta to star. But anyway, here RA is equal to RB is equal to RC, which is equal to here Z1, right? Then here Z1 into Z1 by Z1 plus Z1 plus Z1. So which is here Z1 square by 3Z1. So Z1, Z1 cancel, then you will get Z1 by 3, which is nothing but here, let us consider here it is Z1 dash. Okay, here Z1 dash, these are the star elements. So the similarly for the Z2 dash, Z3 dash also you will get the same. So what is Z1 here actually? 9, right? So then Z1 dash which is equal to, Z1 dash which is equal to here 9 by 3 or J 9 ohms by 3, so which is equal to J 3 ohms. Z1 dash. Then substitute here. So here it is 3 ohms, 3 ohms and 3 ohms. So now let me redraw this circuit to understand for us very clearly. Okay, so just I am converting this circuit into like this, because here both the circuits are same as you can see here. So what are the 3 points? 1, 2 and 3, right? So here let us see here, this is 2 and this is also the point 2, right? So then here also the Z2, where it is Z1 dash and where it is Z2, so Z2 is connected to in between, here it is 3, okay, and here it is 2, okay, then this is also 2, okay, then this is 1, okay. So now as you can see here, where we need to find in between 1 and 2 terminals. So this is also the second terminal. Okay, and let me consider here it is 4. Okay, so this is 3 and this is 4. Now you can see in between 2 and 3 Z2 is there. So same way in between 2 and 3 Z2 is there. Then in between 4 and 3 Z1 dash is there. In between 4 and 3 Z1 dash. How many is 1, 2, 3? So in between 4 and 3, 1 Z1 dash, and in between 4 and 2, 1 Z1 dash, and in between 4 and 1, 1 Z1 dash. The same way here 3. Okay. So just for our understanding, okay, so simple understanding of the series and parallel combinations. So I have just converted this circuit, I have just redrawn this circuit, something like this. Now here it is very easy to identify what are the two resistors connected in series and what are the two, what are the two impedances which are connected in series and what are the two impedances which are connected in parallel. So here as you can see now, the Z1 dash and Z2 are connected in series, okay, and this series combination is in parallel with Z1 dash, right? So which means here, how we can write then here Z1 dash plus Z1 dash plus, so here of course here this is Z1 dash, right? So and this total combination is again in series with this Z1 dash, one more Z1 dash, right? So that's why this Z1 dash, here it is Z1 dash, this one I am writing. So then because this combination and this are parallel, so Z1 dash into here Z1 dash plus Z2 by here the Z1 dash plus again Z1 dash plus Z2. So this is the Z Thevenins. Then substitute all these values here, because as we know the Z1 dash is equal to, here it is J3 ohms, okay, and plus here Z1 dash again J3 ohms into again Z1 dash J3 ohms plus here Z2 is equal to 8 ohms by Z1 dash again J3 ohms plus J3 ohms plus 8 ohms. Then if you simplify this, then you will get here the Z Thevenin's value, which is, let me see, the Z Thevenin's value that you are getting, here it is, Z Thevenin. So by simplifying this, then you will get the Z Thevenin's value. Then finally, by simplifying this, the Z Thevenin's value that you will get here, it is Z Thevenin's is equal to 0.72 ohms plus J 5.46 ohms. This is the Z Thevenins. So here the Z Thevenins, here it is nothing but the ZL. So which is this value, because in the given problem they have mentioned like the maximum power is delivered to this load impedance. So the condition to deliver the maximum power, here it is ZL is equal to Z Thevenins, right? So now we are going to find R Thevenins. Okay, we are going to find V Thevenins, sorry, not R Thevenins, V Thevenins. So for that V Thevenins, okay, so let me write here V Thevenins. Yeah. So in the V Thevenins, anyway here we will be having the input source that has E. So let me write the V Thevenins out, the circuit for the V Thevenins. So here again, here it is the same way, you will be having Z1 dash, and here the same way you will be having, here it is Z1 dash, and again here it is Z2. So just we are replacing the short circuit as usually with the voltage source, so that it will become the equivalent circuit for the V Thevenins. Then here it is, this is the value. Okay, so plus minus, here it is E, and now here it is plus minus. So now here we need to find the E Thevenins. So anyway, this is connected to open circuit, then the current flowing through this particular element is equal to 0. So which means here we can neglect this one now, right? We can neglect this one. So directly we can draw like this. So now what is the E Thevenins? Here it is nothing but the E Thevenins means the voltage across these two terminals. So the voltage across the Z1 dash plus the voltage across the Z2 is the E Thevenins, right? So here also the simply we can apply what is that, the voltage division rule. Okay, so then according to this voltage division rule, here E Thevenins, which is equal, so what is the total voltage? Here it is E, that we already know, E into, so where we need to find in this particular resistance that we need to find, so Z1 dash plus Z2, okay, in across these two impedances that we need to find, by the total impedance, here it is Z1 dash, again Z1, Z1 dash plus Z2. So if you substitute all these values here, then you will get the E Thevenin's value, right? Then finally the E Thevenin's value that you will get, here it is 8.54 at an angle of minus 16.31 degrees. Then what is the maximum power delivered to the load? P is equal to, there are many formulas here, so which is E Thevenin's square by 4 into R. Okay, so R is nothing but again here it is the ZL, okay, or in another words here E Thevenin's square by 4 into, okay, so this is, of course, anyway here in the power we don't consider the imaginary term, so that's why here instead of Z we usually write R only. Then we know the values of E Thevenin's and R value, then you can substitute, then you will get the maximum power which is flowing through the load resistance. So this is how we can find by using the maximum power transfer theorem, we can find the two variables. One is what is the load resistance or unknown load resistance or unknown load impedance. Okay, so where the maximum power is delivered to the load by using the maximum power transfer theorem, and as well as we can also find what is the maximum power that is delivered to that particular unknown load impedance or the load resistance. So this is how about the some numerical problems from the question bank in from the module 3, which is about the networks theorems for the AC and the DC circuits. So in the next class we will discuss the remaining topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.